Slab 5, magnetic braking with Faraday's law. The purpose of the slab is to explore a phenomenon observed when a powerful magnet is dropped straight down conductive tube and falls out the other end. I will collect observational data and model that interaction computationally, and finally compare the results to predictions. So the results from the observed trial average was 1.8 seconds. That was the result of 5 trials. Computational time that it took for it to be in a tube was 2.026 seconds. So here's some physical concepts and equations needed for this law. We have magnetic field of a bar magnet, which is a magnetic field of a dipole, magnetic flux and the derivative of magnetic flux, Faraday's laws, Ohm's law, also involving currents, and Lenz's laws. Here are these important equations I found from the lecture video that we were told to watch to do this experiment. I screenshotted them, and these were the equations that we ended up using, well, that I ended up using in the code. And also just for my personal understanding, especially Ohm's law, comes at the end for the discussion questions. So the setup and the experimental data. So the setup was literally like as shown on the right hand of the screen, literally putting a bar magnet through an aluminum tube. We did this 5 times. So I did this 5 times, and the average was 1.8 seconds. The tube length was 0.28 meters. The foil width was 0.05 meters. Inner radius was 0.017. Outer radius was 0.022. And that's it. So here's a computational model. Some of the stuff here's like my values from this experiment, but other stuff asks for the values from lab 3, for example, mu magnitude. And then the same code from lab 3, the calculating the dipole moment. And then the other stuff is from lecture 43. And then here's us editing, so it looks nice and it looks viewable. And here's what it ended up yielding. Here's the simulation of what happens in real life, what you actually see. And this is the velocity of time versus time graph, in which you can see that the time spent in the tube was 2.026 seconds. So now for the discussion. If resistivity is directly proportional to resistance, then both would be near 0. That means there would be an induced current, and so a large magnetic force on the loop, which happens when there's an induced current because they are inversely proportional. So resistivity and resistance is directly proportional, but magnetic force and induced current are indirectly proportional. So the force on the loop would be extremely strong, which would make the magnet fall at a much lesser speed because it has to counter a stronger force. And if holes or slots were cut into the tube, this would affect the ring currents in the model because it would disrupt the flow of the current, which would decrease it, and in turn that would decrease the magnetic field, which would make the magnet fall at a faster speed. So there are errors because the observed does not match the predicted at all. There could have been an issue with my phone stopwatch, or my measurements of the experimental material might have been a little bit off just due to maybe bad vision. And another thing that could have probably happened was that that my lab 3 stuff could have been wrong. There could have been a bigger mistake there. But other than that, there should have been no errors with this lab. Thank you.